Welcome to Astronomy 103. In this section, we will talk about the lives and deaths of stars and the origin of the elements. Uh, our sun might live about 10 billion years. Right now, it's about halfway through. It's been shining for about 5 billion years or so, and it'll probably shine for 5 billion more. Some stars, however, only live for 4 million years. So, how do we know how stars live and die if humans only been studying stars for the last 2,000 years? Well, that's because we see many millions of stars, and because of that, we see them at different stages in their lives. So the analogy would be if you took an alien from a distant planet and put them in Milwaukee, and the alien saw a baby, a teen, an adult, and a senior. And from looking at these four people, you'll try to put together the life of an average human being. And you could do that if you conclude that the baby, the teen, the adult, and the senior were basically different stages of average human lifespan. So for stars like the sun, the evolution can be broken down to 6 different stages. First, there's the collapse of the gas cloud to form a star. We discussed this previously. Next comes the main sequence, which is also discussed previously. Then the red giant phase, followed by a helium flash, and what's called a second red giant phase, or the asymptotic giant branch. Finally, the sun ends its life as a planetary nebula and forms white dwarf. So it's helpful to understand how stars live and die by keep reminding ourselves that stars are a battle between gravity and nuclear energy. And gravity always wins in the end because it's always unrelenting. Let's start talking about the main sequence. We talked about this before. This is a Hertzsprung-Russell diagram. On the y-axis is the luminosity, or how bright a star is. On the x-axis is the surface temperature, or how hot the star is. Right? And the main sequence is pretty boring because on the main sequence, hydrogen just fuses helium. This is where stars spend most of their lives, right? But where the star sits on the main sequence depends on its mass. So for instance, if we look at the upper right corner, let's get this work. The upper left corner, right, this is a 15 solar mass star. It sits high in the Hertzsprung-Russell diagram. However, as we basically look through much less massive stars, let's say a fifth the mass of the sun, it sits much lower. Our sun sits right about here, but it's a very average star, shining at 1 solar luminosity and a temperature of about 6,000 degrees Kelvin. This solar luminosity is given in solar units, so obviously the sun was shining at 1 solar luminosity. Okay, so let's look at the main sequence. You have a hydrogen burning core in the center, and the energy of a main sequence star is produced by fusion of hydrogen to helium in the star's core. Right. Now, also recall that stars are basically a balance between gravity and pressure. So recall that stars are balanced between pressure trying to push the stuff out and gravity pulling stuff in. The balance between these two opposing forces is called hydrostatic balance. Because stars are constantly losing energy, they would eventually contract if it was not for some internal heat source, in this case nuclear fusion in the center. At some point, stars will run out of fuel. Right? Nuclear fusion relies on nuclear energy, the fusion of hydrogen to helium, the most efficient nuclear energy source in the universe. But even that eventually will run out. Right? But as it runs out, the star will so shine and gravity will take over. Right? By shining, I mean the star radiates away its heat. Right? And so when that happens, the core begins to contract. Now, as it contracts, the core will begin to heat up. So this is unlike other systems that we deal with, right? Um, the star is shining, so it's losing energy. And most of the time, if you heat something up and it loses energy, it gets cooler, right? But what happens is that in this case, the star, as it loses energy, actually shrinks, and as it shrinks, it actually heats up. So as it loses energy, it actually heats up. So remember, this is the negative heat capacity of stars, which is a very unique property of them, which means if you cool it, they actually get hotter. Likewise, if you heat them up, they'll actually get cooler. So this is a red giant star. Inside, you have a non-burning core of helium in the center. So it's called the helium ash. It's produced from the burning of hydrogen to helium. And then surrounding it is basically a hydrogen burning shell, where hydrogen is burning into helium in the shell that surrounds the core. And what happens is that as this thing burns, it actually just deposits more and more helium in this core. The core will get larger and larger. And they have a big, big puffy envelope of basically hydrogen, right? Now, this hydrogen burning shell, right, is just because it's hot enough to burn in the outer layer around the helium core, and because it's burning in the shell, it's called hydrogen shell burning, right? So this phase, when this happens, is actually produces the red giant. Because the core is much hotter and denser than before, the energy basically which is being generated, it generates a much higher rate than it was generating basically when it was burning hydrogen helium in the core, right? And so the hydrogen fusion is much faster in the shell, and the energy shell is much greater. And so because of that, the star will expand. And remember, you add heat to a star, it gets cooler. So that's why the red giant actually gets cooler and becomes what's called a red giant. All right. So the huge amount of energy pouring out from the center region of the star inflates the outer region of the star like a balloon, right? So this star gets up really, really large, right? So when the sun becomes a red giant, outline will extend past Venus and probably will engulf the Earth as well. This is the sun as it is now, right? And the sun is a red giant. By the time the sun reaches a red giant, it will be at the orbit of Earth. It will swell up to about 100 times its own size. In terms of volume, 1,000,000 times its own volume.
We are coming from the deep, cold reaches of the solar system, flying in toward the sun, passing the orbits of Neptune and the binary pair Pluto and Charon. We are seeing our home system as it may look about 5 billion years from now. Looking closely, we see that something's gone dramatically wrong with the sun. Its fuel supply running low, our star now swells in size, becoming a red giant, engulfing the orbits of Mercury, Venus, and our Earth. The sun now goes unstable and puffs off shells of plasma and gas, eventually hurling outwards the components of what will become an immense fluorescent nebula for all the galaxy to see. What remains of the sun now shrinks down to become a dense, cold white dwarf star, the lonely cinder of the former planet Mars as its closest companion.
So that was just a video depicting the red giant. The video starts 5 billion years in the future because the sun is halfway through its red main sequence phase. It's been shining about 5 billion years, so shining for probably another 5 billion more. All right. So why is the red giant red? So because of the expansion of the outer envelope, the photosphere of red giant is cooler and therefore redder than that of a main sequence star. So as the shell around the core burns, all right, in hydrogen shell burning, more helium is added to the core, which I stated earlier. And because of that, this added mass of helium causes the core to contract and makes it basically the temperature hotter, which makes the shell burn hotter and hotter. So eventually it burns hotter and hotter to such a point that actually release so much energy, actually ejects the envelope. And that's basically what that video talked about toward the end. It ejects the envelope and becomes a planetary nebula and leaves this basically cold white dwarf behind eventually. So why is a red? Okay, so another way to understand it is to recall that we have negative heat capacity of stars. So as you heat it up, it gets cooler. If you cool it, it gets hotter. So by adding more energy to the star, which is by hydrogen shell burning, you cool down the star and thus it's redder. So the way it works, all right, is that as the star moves off the main sequence at number 7, it begins basically to contract its core, helium core at number 8, and basically expands outward in hydrogen shell burning, go all the way up to number 9 or so. All right. So let's do a quick, and one interesting thing here is that you notice the red giant sticks around 3,000 degrees Kelvin. It doesn't really change all that much. This is about 3,000, this is 4,000, 5,000 right here. So it starts off 4,000, brings out to maybe a shade above 3,000 or so, and it just stays there. It just rises almost vertically. But you can see it gets much brighter. This is something like less than 100 solar luminosities. By the time it gets here, it's well over 1,000 solar luminosities. So it gets really, really bright, all right? But stays roughly the same temperature. And because of that, it has to get much, much larger. Okay, so here's a quick summary of red giant phase, right? At the inner core has fused the helium and begins to contract, heat up. What happens is now is that the core, the outer part of the core actually becomes hot enough that drive a furious rate of fusion of hydrogen and helium in the shell around the core. And because this prodigious generation of energy from fusing hydrogen helium in the shell, the outer part of the star vastly expands from the combined energy of contraction and the shell burning. And the core will continue to contract as the shell adds more and more helium to the central core. Right. So the red giant stage will end when the core is finally hot enough at roughly about 100 million degrees Kelvin to fuse helium to carbon. Right. So this is the helium reaction, which is known as triple alpha. All right, reaction. That's because alpha particles are essentially helium nuclei. So you have basically 3 heliums, 1, 2, 3. That's why it's called triple alpha. And the way it works is that basically when they fuse, right, you take 2 helium nuclei first, they fuse, they make beryllium-8. This is very unstable. It doesn't really last very long. Most of the time when it fuses to this, it actually just breaks up back into helium-4s, right? But every now and then, another helium comes just in time to fuse. This is basically just-in-time reaction, and basically it produces carbon-12. And this is basically excited but stable, and will release some energy in terms of a gamma ray, right? And so because of this, all right, this extra energy is basically what takes basically 3 helium atoms, makes 1 carbon atom, and releases some energy. And this only happens at around a temperature of 100 million degrees Kelvin, right? So when this happens, right, so for all stars which are larger than maybe 40% the mass of the sun, the temperature at some point will be hot enough, reach 100 million degrees Kelvin, to ignite basically helium into carbon. All right. So this is the 3 heliums that produce the single carbon atom. And when this happens, this begins explosively throughout the core, right? And so the burst of energy that is released is called helium flash, right? So what happens is that when this happens, you generate energy in the core itself, right? Before you were just basically generating stuff around the core. Now you're generating energy in the core itself. And because the core will re-expand, right? The hydrogen burning a shell, because it re-expands, remember adding heat, it gets cooler. And as a result, the hydrogen shell burning in the shell slows down because the shell is now cooler. And the outer layers of the star will contract. So add heat, you take away the hydrogen shell burning heat, and what happens is that basically the entire star will begin to contract and in fact heat up, but it will be less bright now. Okay, so this is basically the helium flash. So you flash helium and basically it gets less bright because it goes down in brightness, and it gets hotter, right? Okay, so basically the helium flash produces the expansion and cooling of the core. Okay, and because of the negative heat capacity of the star, adding heat to the core will actually cool it, which will basically allow the entire rest of the star to basically heat up. Okay, now this happens happily long. The hydrogen, after the helium flash, starts will burn helium carbon in its core, and it basically continues until all the helium cores turn to carbon. Now the fuel in the core is exhausted, and again gravity takes over. So the core will start contracting. So with this fusion, it halts the contraction of the core, and so when this fusion stops, the core once again begins to contract. So the contracting core heats up and ignites now helium in the shell around the burn. So this helium will burn in the shell, right? Now this intensely hot inner core drives a ferociously rapid burning of helium to carbon in the shell, and it also basically produces a second hydrogen burning shell around the helium. So you have 2 shells now around it. So now you have an inner core, you have a helium burning shell, and a hydrogen burning shell. That's a lot of energy. You got 2 shells basically burning energy for you. Okay, and so basically it starts going up again. This plot is actually not that well done. It just comes down quite a bit further, right? And when this comes up, it's the hydrogen astatite giant branch phase, or the second red giant phase. And in fact, it actually is much closer than this plot shows. Actually, it will actually hug this red giant phase, like almost up, but it'll go a little past basically where this thing ended. Right. So release a lot more energies and again the star will expand in the second red giant phase. So now you have 3 sources of energy: contraction in the core, the burning of helium to carbon in a shell, and basically hydrogen to helium in another shell, right? So this star will actually become much larger than it did the first time, right? And so eventually by increasing the temperature of the core, the outer layers are essentially blown off out of the star and produces a planetary nebula.
They begin in clouds of dust and gas so far away, we would need 100,000 years to reach them. Gravity gathers hydrogen gas and particles of dust, and the clouds grow more dense. Squeezed tighter, the hydrogen heats up to a fantastic 18 million degrees Fahrenheit. Nuclear fusion turns hydrogen into helium, and the fire ignites. A star is born. Astronomer Michael Shara compares a star's life cycle to our own.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart.
Of course, a star may live for billions of years, and stellar age has nothing to do with lifestyle or heredity. It's all about size. Smaller stars burn cool and dim. When their fuel burns out, they just fade away. A medium star, like our Sun, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core harder, the star grows hotter and the outer layers puff up, engulfing nearby planets in its fiery demise. Finally, the outer layers blow off into space, and a dense solid core remains. This white dwarf is a dying star. A bigger star, say twice the weight of our Sun, lives hot and dies young. It burns through its fuel in just millions of years, and it doesn't go quietly. There's more material here for gravity to constrict. The star goes out with a bang called a supernova. Gravity packs the remains into material far denser than white dwarfs, called neutron stars. A teaspoonful of this stardust weighs more than a cruise ship packed with people. Some enormous stars gone supernova become so dense they turn into black holes. Think about it. A massive explosion leaves gravity unchecked, and matter is squeezed into something unseeable, stretching as far as miles and weighing incomprehensible amounts. Got it? Invisible but deadly, pulling in matter all around it. Even light can't escape. Not to worry. Supernovas are rare. A galaxy like ours, of 100 million stars, may experience only one exploding star in a century.
All right, so let's keep talking about the death. So that video basically presents a short story of basically how stars like our Sun will live and die, and a preview of basically how stars much more massive than the Sun will live and die. So let's talk about the last part, which is the ejection of the planetary nebula and white dwarf formation. So with the hydrogen shell gone, the hydrogen and helium burning shells will eventually run out of fuel, and the carbon core slowly cools off. So if gravity have its way, then the carbon core will eventually contract to a high enough degree, heat up and ignite. But before it does, something called degeneracy pressure will take over. So let's try and understand what degeneracy pressure is. If you cram too many electrons into a small enough space, the electrons' quantum mechanics prevent you from squeezing them any tighter. This is what's called degeneracy pressure. In fact, degeneracy pressure is all around us. All the solid materials on Earth are solid because of degeneracy pressure, right? So if you ever touch a piece of metal, right, and you try to push against it, the metal will resist. And the reason why is that you try to push electrons close to each other, and because of that, because of the degeneracy pressure, the electrons will prevent them having. So degeneracy pressure in metals gives them the resistance to compression, right? I put a heavy metal thing, Black Sabbath thing, but that's just as a joke. All right. So to support the star's core against gravity, degeneracy pressure has much larger than it would have to be on any metal on Earth, right? And so stars which are supported by this degeneracy pressure are called white dwarfs. So the Sun eventually will end its life as a white dwarf. it'll compress itself maybe 60% of its mass or so, or 50% of its mass, will compress itself to something like the size of the Earth. So typical white dwarf rays are roughly about the radius of the Earth, and its density is roughly about 5 tons per teaspoon. So that's pretty substantial, right? A star smaller than 4 solar mass will end its life as a planet by ejecting planetary nebulae, sending white dwarfs, right? And so white planetary nebulae are thus found usually around a lot of white dwarfs. So there it is. There's a white dwarf. There's an arrow pointing to it, and around it you see the big shell material. This is called the planetary nebula. There's another example. There's white dwarf in the center. It's really bright, and ignites. It doesn't ignite, but it shines on the planetary nebula, so we get to see it. Here's another great example of planetary nebula. A lot of times these things show basically conal outflows. It's like you see 2 cones. You can imagine expanding away from the central region. Right, here's another great example of bipolar outflow, right? So this out one pole, out the other pole, right? But again, this is ejection of material, and there's that white dwarf in the center. So toward the end of its life, it burns so bright that it sheds basically all this gas as the planetary nebula. And once it runs completely out of fuel, it basically contracts, cools off, right? So now it's coming down. It's still very, very hot, right? But its brightness is slowly decreasing and becomes a white dwarf, right? And this star will eventually cool off to such a degree that it becomes a black dwarf. It's not a black dwarf, it's always a white dwarf. It just gets cooler and cooler, right? Now, white dwarfs are interesting, all right? Because a lot of times they can be near other stars, and sometimes they can be so near that they actually pull off material off of the other star. So, in a close binary, when one star becomes a red giant, so it becomes sufficiently large. So let's say there's a white dwarf here, and this is a normal star, and the star evolved, got older, ran up red giant phase. Eventually gets so puffy and large that actually this material can be pulled off the red giant and basically form some material that falls onto the white dwarf. So the hydrogen from the surface of this star falls onto the white dwarf. Now, as it builds up, all right, the hydrogen builds up, it just stays on the white dwarf initially, but as it builds up, it gets hotter and hotter, it gets denser and denser, and eventually what will happen is actually it will just ignite spontaneously, all right, and suddenly fusing. So this is called a nova, all right? It's essentially the sudden fusion of hydrogen and helium on the surface of the white dwarf, essentially a nuclear bomb on the surface of the white dwarf, right? Okay, and because of this stuff, what happens is this hydrogen burns the helium burns the carbon, etc. It can actually increase the mass of a white dwarf in principle. And so the white dwarfs can start building a mass from accretion material from the companion. Now, you can't keep adding mass to a white dwarf forever. There is a maximum mass for them, which is about 1.4 solar masses, because beyond this amount, there's a maximum amount of pressure that the electrons can push back on. Okay, but there's no limit on the maximum gravity. And so because of that, beyond 1.4 solar masses, gravity will win and cause the white dwarf to collapse. This is called the Chandrasekhar limit. It's named after this guy, this Soumdarajan Chandrasekhar. This limit was discovered in 1930 by a 20-year-old student who was on a ship, all right, traveling from India to England, where he was going to do some graduate work with a famous astronomer called Sir Arthur Eddington, all right. And on this trip, he decided to derive this limit, right? So as a white dwarf approaches its maximum mass, the center can get so compressed that it will actually ignite carbon, fusing into other elements. And because it fuses suddenly, this causes a runaway nuclear reaction. And it will burn up the white dwarf in one spontaneous, humongous explosion. Here's an example of this. So this is carbon detonation of a white dwarf, which is called Type 1a supernova. Right. Here's a continuous simulation of one of these supernovas. So there's some initial burning that sets off And because it's hotter, it will just rise. And it'll cause a big plume to rise off the center of the white dwarf. And once it happens, it'll break out in the surface. And this is just a slow-mo matrix video of it. And what will happen as it breaks out of the surface, it'll start flowing around the white dwarf and hit the other side and cause another ignition. Let's see if we can see that. Here it goes. Here it comes spraying around. It's going to spray around the other side. All right. One more matrix rotation for us. Now keep an eye on the opposite side from where the initial ignition happens. When we zoom out, it's going to compress exactly. See that flow? It all comes together all at once, basically. It's like a magnifying effect. All right. And there, it can generate conditions to actually ignite the star in one titanic explosion. I mean, it'll blow already, but like this is just going to make it much more powerful. I don't think this one actually shows the explosion. Maybe it does. Yep, that's it. Okay. So type 1a supernova can be very bright. They can be bright as the entire galaxy. So the example of this is a supernova going off, right? There's a dim, and bright. And then when it reaches this phase, it's comparable to the brightness of the galaxy. It's pretty substantial, right? So there are some famous supernova remnants, basically remnants. This is called Tycho, named Tycho Brahe, who discovered it basically looking at one night. So the name of Tycho Brahe, who observed this thing in 1572. All right. So when you see how bright they shine, you might ask yourself, why do these supernovas shine? So when supernova type 1a, go off, all right, carbon and oxygen is burnt in the heavy elements, releasing energy. Most of it burns to silicon and nickel 56. Now, nickel 56 is interesting. Nickel 56 is radioactive and decays over a few weeks. Right? And this radioactive decay produces heat, which the expanding supernova emits as light. Right? So they're essentially they're different from regular stars. Regular stars shine because of nuclear fusion. Right? Supernova are basically powered by nuclear decay or nuclear fission, just like nuclear reactors on Earth. So they're essentially giant nuclear reactors in the sky. So nickel 56 decays iron 56, which is common iron on Earth, right? So type 1a supernova is responsible for between 50 to 75% of all iron in the universe and on Earth. Okay, here's some typical light curves for supernova 1a. They get really bright and then fade away, right? And this fading part is characteristic of radioactive decay. Now, it also turns out that you can rescale all these things in such a way that they look like each other. So type 1a supernova are also known as standard candles. And because they're standard candles, you can use them to measure distances in the universe. So for instance, this is famous example from 1998, measuring basically the distances using supernova, and you can get there's a difference between the stuff with dark energy, without dark energy. This is the first indication that the universe is filled with dark energy. And because of this discovery, these three physicists, Saul Perlmutter, Brian Schmidt, and Reese, won a Nobel Prize in 2011 for the discovery of dark energy, exactly using these type 1a supernovas. Right. Okay, so let's talk about stars more massive than the sun. Right. So these, in fact, will not form white dwarfs. So more massive stars will build heavy elements up from carbon. Right. So for instance, like between 0.4 and 4 solar mass, hydrogen burns helium, helium burns carbon. This is basically what we just talked about before. Okay. Above 4 solar masses, carbon will burn to neon, sodium, magnesium, and oxygen. And beyond this, so you have carbon fusion. And beyond 8 solar mass, neon and oxygen fuse to form higher mass elements up to and including iron. Okay. So stars with lower masses produce only carbon. Okay. Stars with higher masses produces iron. And the way that works is that you see here, there are two shells, right? There's a hydrogen to helium burning shell, helium carbon burning shell, and then carbon ash in the center. On stars much more massive, there's many more layers. There's the hydrogen shell, then the helium shell, then the carbon shell, then the oxygen shell, then the neon shell, the magnesium, silicon shell, and finally at the very end is the iron ash. So basically you have this entire onion skin of stuff which is producing energy. Okay, so here's an example of a 10 solar mass star. So the hydrogen burning will last about 10 million years. Then you get the helium shell burning, or red giant phase there. It will last for 1 million years. Then the helium flash, helium core burning, that's lasts for another million years. Then you have helium shell or hydrogen shell burning. All right, this builds up the carbon core. All right, it lasts for about 100,000 years. Then you have carbon ignition, right? And with hydrogen helium shell burning, that goes for basically about 10,000 years. Now you're going to get to basic stuff that lasts only a very short period. Oxygen, neon core burning, all right, plus everything else in shell burning. That only lasts a few years. When this happens, beyond this, you get silicon burning. That only lasts for 1 day, right? When you have silicon burning, you're basically burning silicon to iron. And once it basically approaches Chandrasekhar limit, which is 1.4 solar masses, then basically the core will begin to collapse and the star will explode as what's called type 2 supernova. Right? And the reason for this is that iron is the most stable element. It's the most tightly bound nucleus. And so because if you in the core of a star, if you're starting to try to fuse iron, you can't actually get any energy out of it. That's it. Right? You are done. You actually end up cooling the core, which causes it to contract even more. So heavy elements up to iron are built in the cores of stars. Okay. So all the atoms in your body that's heavier than helium, right? And there's not much helium in your body, were force formed in a star, and nearly all the atoms being helium and iron were forged in these sorts of nuclear fires. So in fact, we are all basically made of stardust, right? Because stars had to produce all the elements that make us up. Right. So at the end of the life of a massive star, more than 6 to 8 solar masses, the core is iron and nuclear around the core. Just add more iron to it. But iron is more stable, as we said before. It won't fuse to make anything heavier. And now the iron core acts as a white dwarf, right? And it will contract until it's held apart. But it will contract basically, but it's only held up by degeneracy pressure. So once it hits past the Chandrasekhar limit, 1.4 solar masses, the iron core collapses and basically will blow off the rest of the star. That's what they have here. So as the core collapses, electrons are pushed down the nuclei, and the core collapses from the size of the Earth to the size of Milwaukee, about 20 kilometers or 13 miles an hour. 100 times more energy is released in these few seconds by the collapse than the stars ever did over its lifetime. Right, so this creates a neutron star. A star is composed of neutrons. Basically, a star is almost a giant atomic nucleus. Okay, let's see if we see this here. So this is what we have here. So you have the iron core in the center. Iron core, as you zoom in, it begins to collapse. As it collapses, what happens eventually at some point, neutron degeneracy pressure takes over. And when neutron degeneracy pressure takes over, it actually stalls the collapse. And like a bouncing ball, it will basically bounce back up and pressure shockwave through the rest of the star. So here's how this iron core begins to collapse, as we stated earlier. It takes 1 second for the core to collapse about 20 kilometers. Now nuclear forces take over and stop the collapse. And so like a rubber ball, basically hitting the ground, right? This is called a core bounce. And it sends shockwaves in the rest of the collapsing star. The core, which is now a neutron star, is so hot that it releases more energy in neutrinos, 100 times more energy than the star produced over its entire lifetime in 10 seconds. All right. So shockwave stall, there's simply too much material in the way, and you couple basically about 1% of the energy of neutrinos to re-energize shock in order to basically blow up the star. So here's a computer simulation of that process in action. Core is going to collapse. Let's see if you can see it. And you can see it bounce. All right, here it comes. Core is collapsing, core is collapsing. Hopefully there's a bounce. There's the bounce. I think the bounce is coming. Yeah, there we go. And now what happens is that now neutrinos are being released. And because of that, it's starting to heat up the material around the core. So this is this region right here. If I could get the mouse going to work. There we go. This region right here is the stall shock. And it's being heated by the neutrinos. And as the neutrinos heat this thing, it gets hotter and hotter, hotter and hotter. And eventually it will heat up to such a degree that the shock will actually be reinvigorated and push out through the rest of the material. You gotta keep in mind what's happening. What's stalling the shock is all this material falling back on the star, right? Keeping it from coming out. And so you have to basically re-energize this thing in order to allow it to happen. So now it's appropriately re-energized. It starts to drive this powerful shock through the rest of the star. Nothing else is going to stop it now. It's going to basically break out and blow up the entire star. Okay, and here's an example of one of these supernova. This is a supernova that was observed in 1054 and leaves behind this thing called a Crab Nebula. I'm not sure I see the crab there. You look there, Mike. But it's interesting, in this thing, you see the central neutron star, or what you call pulsar instead of it. Right? So the process of core collapse supernova creates all the other elements heavier than nickel, including gold, platinum, uranium, etc. Okay, because you need a lot of energy to produce this stuff. So you can't produce it by fusing it, all right? You produce it by pushing shock through everything and causing it to spontaneously fuse. So you get much. So that's why gold, platinum, uranium, all this heavier elements are typically much rarer than iron. So because the process of core collapse creates a bunch of these neutrons from making neutron star, it can capture onto nickel to create heavier elements. Okay. So elements that form low mass stars stay inside the stars. Elements having helium are distributed by the supernova explosion, blow apart the most massive star. Near everything you knew except hydrogen was born, the massive star blew itself apart in a supernova. Okay, so supernova weight elements heavier than helium get out of stars, where they form and are distributed throughout the universe. How about more massive explosions? So for really massive stars, bigger than 50 times the mass of the sun, they may end their lives in the most violent explosions in the universe. Okay, at these masses, the 1.4 solar mass neutron star in the center cannot re-energize the shock. And so what happens is that all the stuff basically falls onto the star, and the stuff just piles onto this proto-neutron star and builds up a mass. And around 2 to 3 solar masses, something else happens. The proto-neutron star basically becomes a black hole. So here it is, basically become a black hole. There's my proto-neutron star. It's all the stuff is falling on it. It's collapsing. It became a black hole, and now it's basically re-energizing what's called a jet. And this jet will punch its way through the star. Let's see, there's the jet. It's coming through the surface. Boom. It's going to blow apart the entire star, release this jet energy. And if it points towards it, you see it's something very, very bright. Okay. And so these explosions are called hypernova, because they're even more powerful supernova. And the jet points toward us, it produces what's called a gamma ray burst. So basically, you see this stuff. You see there's a jet coming from the black hole in the center of the star that just was recently produced. Jet basically punches through, and we look toward the direction of the star. Gamma rays are produced from the inside the jet. All right. As it breaks out of the stellar envelope, and we see these gamma rays here on Earth. Right. So the gamma ray bursts that we observe on Earth come in two varieties. All right, short and long bursts. The hypernova is one that powers the long bursts. So these gamma ray bursts gives off more energy in 1 second than the entire supernova explosion. And they were first detected by satellites in the 1960s looking for illicit nuclear testing. So the US launched a bunch of satellites in the 1960s looking down at Earth, looking for basically gamma rays that were produced from nuclear explosion, and they found them, right? But it was coming from the wrong direction, it was coming from the sky. And it was not until 1999 that the true nature of these gamma rays bursts were revealed. Okay, so let's talk a little about age of star clusters, all right? So you can use our knowledge of stellar evolution to tell you how old a star cluster is. Okay, so remember, more massive main sequence stars evolve faster, live shorter before they go up the red giant phase. Okay, and what's interesting about a star cluster, all the stars roughly form roughly the same time. Okay, here's one star cluster. This is AAT, the Austrian Telescope 25. Okay, so which is jewel box, a young open cluster. Here's another one, M11. It's about 500 million years old. I don't know what that is. Let's see. How old is this one? This is even younger ones, NGC 203293. Okay. Some old globular clusters. This is M10. So you can see how red is, the red stars there. Another old one. This is basically M13. All right. Okay. So the reason why we can do this is that the stars and star clusters all form roughly the same time. So if a star cluster is 100 million years old, the main sequence stars that live for 100 million years should be leaving main sequence to become red giants. So this is called the main sequence turnoff. Right. So here's some young clusters. You see it goes all the way up here. There's just a few stars out here, basically, which is off the main sequence. Most of the stars are in the main sequence, right? These are pretty massive stars. However, you get to older clusters, what happens is that these stars all lived and died already, okay? And so the present day a few of these clusters are basically starting to fall off. So this is 100 million years. These stars are living 100 million years. Now they're going through a giant phase. If a cluster is 4.25 billion years old, however, it's even lower mass stars actually coming off the main sequence at that point, right? Because these stars have already lived and died, so you don't see them anymore. Okay. So this is HR diagram of a young cluster. There's a turnoff. It's barely seeable. Old Glauber cluster is a beautiful turnoff right here, right? Okay. And so by looking at stars of this age, you can tell basically how old a cluster is. Okay. So by looking at the HR diagram of a star cluster, you can tell where the main sequence turnoff is and thus get the age of the star cluster. For Glauber clusters, there are stars that don't quite fit this simple picture. These stars are known as blue stragglers. So I'll show you, these are the blue stragglers right there. Look, they're too blue, right? These stars, they should have lived and died many years ago, right? But they're still there. Right, so why is that? Okay, so it's thought that they're renewed stars, right? So stars that merge with other stars to make a more massive star. So it shines brighter and hotter and thus looks a lot younger than it actually is. Okay, and